You think gravity pulls you down? Think again. For centuries, we've had it all wrong. Gravity isn't some invisible force yanking objects together. It's a profound distortion in the very fabric of reality. In this video, we're tearing down the textbooks and revealing the mind-bending truth. How gravity actually works, not as a pull, but as a cosmic bend that shapes everything from falling apples to spinning galaxies. Prepare to have your understanding of the universe completely reshaped. At its most fundamental level, modern physics describes gravity not as a force pulling objects together, but as a curvature of spacetime caused by mass and energy. Massive objects, such as planets and stars, warp the fabric of spacetime around them. This distortion dictates how other objects, including light, move through that region. It is this geometric effect that we perceive as gravity. Spacetime is a four-dimensional construct combining the three dimensions of space with the single dimension of time. In Albert Einstein's general theory of relativity, spacetime is not a fixed, rigid background, but a dynamic entity. It can be stretched, compressed, and curved by the presence of matter and energy, directly influencing the paths of everything within it. The more mass or energy an object possesses, the greater its influence on the surrounding spacetime. For instance, the Sun's immense mass creates a significant indentation in spacetime, causing Earth and other planets to follow curved paths. These paths are not due to an invisible pull, but rather to the planets moving along the shortest possible trajectories within the warped geometry. Objects in a gravitational field follow what are known as geodesics, which are the closest equivalents to straight lines in curved space. In the absence of other forces, an object will naturally follow a geodesic through spacetime. What appears to us as an orbit around a star is, in this view, an object simply following a straight path along the contours of curved spacetime. While Isaac Newton's law of universal gravitation accurately describes many gravitational phenomena, especially at everyday scales and velocities, it treats gravity as an instantaneous force. Einstein's theory provides a more complete and accurate description, particularly for strong gravitational fields or objects moving at relativistic speeds. Newton's theory can be understood as an excellent approximation of general relativity under weak field conditions. A key prediction of general relativity is the existence of gravitational waves, ripples, in the fabric of spacetime itself. These waves are generated by accelerating massive objects, such as colliding black holes or merging neutron stars, and travel at the speed of light. Their direct detection in 2015 by the LIGO experiment provided profound confirmation of Einstein's theory. Black holes represent extreme manifestations of gravity's warping effect on spacetime. Within a black hole's event horizon, the curvature of spacetime becomes so intense that nothing, not even light, can escape. This singularity, the black hole's center, represents a point where spacetime curvature is theoretically infinite, according to general relativity. Gravitational lensing is another observable phenomenon predicted by general relativity. Massive objects, like galaxy clusters, can bend the path of light from more distant sources as it travels towards an observer. This bending acts like a cosmic lens, distorting, magnifying, or even multiplying the images of background galaxies, offering a unique tool for astrophysical research. Gravity also influences the passage of time, a phenomenon known as gravitational time dilation. Clocks in stronger gravitational fields run slower than clocks in weaker fields. This effect is crucial for technologies like GPS, where satellites orbiting Earth experience weaker gravity and thus their clocks run slightly faster, requiring precise relativistic corrections. Despite the success of general relativity, a complete understanding of gravity remains elusive, particularly in reconciling it with quantum mechanics, the theory governing the other fundamental forces. The search for a theory of quantum gravity aims to describe gravity at microscopic scales and extreme energies, potentially revealing a unified framework for all physical interactions. Thanks for watching. Please subscribe to our channel.